Hello, folks. As I said, there would be assignment. There would be some sort of thing to take up your otherwise free day. So, the first thing I'm going to talk about is the main thing: watching, uh, watching the video that covers the rest of this chapter. Yes, I made it into work. If you can't already tell, with the help of a little bit of warmth, heavy coats, a little bit of snow boots, but a little bit of grippy things for make sure I didn't slip. So on Google Classroom, you already have this available. So you'll go to classwork, and if you scroll down to the chapter 13 lecture, I want you to finish watching the colligative properties. This should open it up. It's in YouTube, and you can watch the rest of the chapter's material. Now, unless the weather changes drastically in the next day or so, I can't imagine us having lab tomorrow. I can't imagine Bethel's going to be open unless we have a huge melt off, and if things do melt, it doesn't refreeze. So I can't imagine Bethel being open tomorrow. If it's closed on Wednesday as well, there might be another video. But in the meantime, so we will have to make up that lab another time. We'll figure out that practicum. So we'll plan on, I want you to go ahead and work on the pre-lab for the colligative properties lab. That's going to be on in February. So that lab is essentially going to be one where we're going to measure the freezing point or melting point of a organic solid, and we're going to dissolve an unknown organic solid into there and see how the freezing point is depressed. And by measuring this change, knowing the freezing point depression constant, we will be able to calculate the molar mass of our unknown. It's going to be like some problems I'm going to assign you right now. So these problems, I'm going to work them out. But I also want you to give them a try first. So we'll read this through. I'll give you a chance to pause the video, see if you can figure it out on your own. If not, I'll work them out fully either way. So first one. This one is just like the chapter in the chapter 12 homework. A liquid has a vapor pressure of 52 torr at 30 degrees Celsius. The vapor pressure increases to 175 torr at 40 degrees Celsius. What is the liquid's enthalpy of vaporization? That's question 1. Question 2, at what temperature is the normal boiling point? So the equation we need is ln of P1 over P2 equals delta H over R 1 over T2 minus 1 over T1. R, if you don't already know, is 8.314 joules per mole Kelvin. And we need our temperatures in Kelvin. So P1, I'm going to say 52 torr. T1, 30 plus 273, makes that 303 Kelvin. P2 is 175 torr. And T2 at 40 degrees would be 313 Kelvin. So you have all you need to start to solve this. So I'm going to give you a chance to pause the video if you want to try to work this out. Then you can see, as I work this out, how well did you do. So get ready to pause in 3, 2, 1. Okay, so let's work this out. It didn't really matter which one we called P1 and P2 as long as we keep the T1 and T2 together. So ln of 52 over 175. It doesn't matter the units as long as I keep them the same. So torr and torr equals delta H over 8.314 1 over 313 minus 1 over 303. So I'm going to start by evaluating parts that I know. So ln of 52 over 175, or take the natural log of that. I get negative 1.21, we'll say 35. Then I say 1 over 313 minus 1 over 303. And I'm going to divide that by 8.314. I'm going to turn that into scientific because that is a pain. So let's times. Try to figure out. Okay. I think that's right, but I'm going to double check. So that might be negative 1.268 times 10 to the negative fifth. 8.314. Okay. Yes. So that's a really small number. But that is in units of 1 over joules per mole. Okay. And that's times my delta H. So at this point, negative number. Let's figure out what our enthalpy is. So I'm just evaluating, I'm dividing both sides by this. So my negative, okay, we'll just do negative 1.2135 divided by negative 1.268. I hit the double E button to make that easier, negative fifth. And I have an enthalpy value. Delta H is going to be equal to, and this is important, it should be positive, 957.0, and we're going to round it to. That's joules per mole. If I were to convert that into kilojoules, it would be 95.7 kilojoules. But I'm going to leave that. So now that I have that value, I can answer the second question. The second question, of course, is where is the normal boiling point? The normal boiling point is the point where the pressure, I'm going to say P3, is equal to atmospheric pressure, which is 760 torr. So we're wondering where T3 is. Now, we do not care whether we use P1 and T1 or P2 and T2. The key is just going to be, I will probably want to plug my T3 in for there. It's going to make my life a little bit easier. So I'm going to just arbitrarily choose P1. So we'll take P1 as 52 and T1 as 303. But it really doesn't matter whether I choose P1 or T1, P1 or P2 to get that. So ln of 52 over 760 is equal to, and here's why we needed the first part, 95702 divided by 8.314. 1 over T3 minus 1 over 303. So let's start by evaluating what we know. Start with ln of 52 over 760. Okay, that gives us negative 2.682. Okay. I'm going to get that to the other side. So cross multiply. I'm going to cross multiply that value by 8.314. H over T3 minus 1 over 303. I'm just being lazy. Cross multiply by 8.314. Divide by my 95702. And that gives me negative 2.330 times 10 to the negative fourth. That is equal to 1 over T3 minus 1 over 303. Next, I would add 1 over 303 to both sides, which gets rid of that. And I'm left with 3.067 times 10 to the negative third, 1 over T3. Finally, I hit the inverse button. The inverse button is at x to the minus 1. When I hit x to the minus 1, I'm going to flip that. So now our temperature is 326. 326 equals T3. And if I convert that into Kelvin, from Kelvin into Celsius, the boiling point occurs at 53 degrees is the boiling point. Which is not super high, but considering how much it jumped in 10 degrees, and it's a exponential increase, that is not unexpected. So hopefully you got something like that as your answer. Looking at problem 2. Problem 2, that problem was from chapter 12. This problem is from chapter 13. Looking at freezing point depression. This is the type of math we will be doing this is the type of math we will be doing in lab. So camphor C10H16O is a non-ionizing solvent with a high freezing point depression constant of 40 degrees C per molal. If camphor normally melts at 179.8 degrees Celsius, what would the new melting point be if it included 1% impurity of isobornyl C10H18O? 1% by mass. So our equation is delta TF equals negative I KF times my molality. We've said that KF is about 40 degrees Celsius per molal. We're saying the T initial is 179.8, and it's non-ionizing, so that means our I is equal to 1. So our goal is to find the molality and then use that to find our freezing point depression. So we have to do that. It's 1%. That means for every 100 grams total, so for 1 to 99. So 99 grams of camphor means 1 gram of isobornyl. So C10H16O versus C10H18O. Okay, you have all you need to do to solve this. Now, one last thing. Molality, remember, is moles of solute over kilograms of solvent. Now, I'm going to ask you to pause it now and then try to solve this, and then I will work it out for you. See how well you did. Pausing it now. Okay, so now hopefully you've tried this on your own. So the first thing to note is the kilograms of solvent. Since it's a ratio, we can just say, well, there's 0.099 kilograms. You essentially divided your 99 grams by 1,000. So that's solvent. So it's not out of 100 total. It is out of 100 total, but we don't care about the total. We care about how much of it is camphor. So we need to find, well, what is the moles of the C10H18? So 1 gram. So we got to figure out what is the molar mass real quick. So molar mass of C10H18O. We have 12 times 10, 1 times 18, plus 16 times 1. So doing that real quick, 12 times 10 is 120, plus 18, plus 16 is we have 154 grams per mole. You'll notice it looks weird because I still have it in scientific notation. I think I'm going to change it back. Okay. So 154 grams per 1 mole. The moles, of course, would be 154. 0.00649 moles. Now, so our molality is going to be 0.00649 divided by 0.099. 0.099. You have a molality of 0.065. Well, let's say we'll round out 0.656 molal. Okay. So 1% impurity. Percent impurity by mass. So let's keep working. So molality. So we have 0.0656 times 40 is going to be times -1. Going to be how much would my freezing point go down by? It would go down by -2.62 degrees. So my new freezing point, that's my delta T, is equal to the T final minus the T initial, 79.8. So my new freezing point, I'm doing it wrong, so it'd be positive version. So my new freezing point has dropped to 177. We'll say 2. That is my new freezing point. So that's my new freezing point. It's not a huge change. But keep in mind, it's 1% by mass impurity. 1%. A very, very small impurity causes this guy to drop by a huge amount. So that is an example of this problem. Last problem I'm going to give you to work out, kind of practice, is this guy. Water. 100 grams of water is mixed with 10 grams of a chloride salt. If water has a KF of 1.86, what is the new freezing point? And the new freezing point is -5 degrees Celsius. What is our formula for this salt? So what is the molar mass of this salt? Now, since I told you it's a chloride, there's a big hint. we only have so many that it's ionizing. So same equation. Delta T is equal to negative I Kf times M. That's a salt. It's probably going to split up, so I may not be 1. I've given you that Kf is 1.86. The Tf is negative 5. Hopefully you know that Ti is 0 degrees Celsius. So that means my delta T is going to be negative 5 minus 0, or negative 5. So this is a problem very similar to what we would do in lab. We know the weight of our solute. We know the weight of our solvent, so we can figure this out. So this one's a little bit more challenging because I is not 1. But so I'll give you a few minutes to work this out, so go ahead and pause the video now. Okay, so we have negative 5 equals negative I times 1.86 times M. Now, we can try various I's. Let's start with just an I of 2. What would we get if we have I of 2? If it was something like sodium chloride or potassium chloride, or would be rubidium or cesium, all of these would have an I of 2. It would split into the cation and anion, I of 2. If it was something closer to, say, beryllium chloride or magnesium chloride, so on, so you would have an I of 3. So we can try it with an I of 3 and see what comes up. So the first step, I'm going to do I of 2. So negative 2 times 1.86 times M. So I am just isolating my M. So negative 5 divided by negative 2 divided by 1.86 gives us a molality of M would be 1.344. Now that's moles per kilogram of solvent. Moles per kilogram of solvent. Moles of salt per kilogram of solvent. Now we're told that the kilograms of solvent is 0.1 kilograms. So this is equal to 0.1 kilograms per mole. So cross multiplying, you would get this to be 13.44 moles in that in that 10 grams. Now, I think I did something wrong. Okay, let's see. We'll see how it works out. So that's equal to the moles. That seems a bit high. 2.5. Okay. Okay, so now with 10 grams. So if we take the grams and divide by the moles, this would give us the molar mass. Yeah, I definitely screwed something up. Let's see. Yeah. Divided by 9.1. Okay. No. No, it should. Okay, we'll see. 10 grams per this many moles. And that should give us the molar mass. 10 divided by 13.44. No, that's definitely screwed up something. Let's see what is going on. Okay. Yeah. Oh, I know exactly what I did wrong. No, that's right. That's 0.1. That's what I get. Everyone makes mistakes. I was multiplying by 0.1. I divided by 0.1. I need to multiply by 0.1. So my moles are not 13.44. Hopefully you saw that if you had worked it out. It's 0.1344. So 10 grams divided by 0.1344 grams and moles, that would give us a molar mass of 74.4 grams per mole. Now, sodium is 23, chloride is 35.45. Let's see, what do we got? Lithium, I guess I could have had lithium chloride. Lithium would be what? 7. So 7 plus 35, we'll say, no, 42. 23 plus 35, that's 58. So no. 39 plus 35, well, that's 74. So potassium chloride is a definite possibility. Rubidium, which would be 85 plus 35, definitely not 120. Let's try it real quick. What would you have if the I was instead 3? How would that have changed it? Could we get a possibility? 5 equals negative 3 times 1.86 times m. 5 divided by 3 divided by 1.86. So my m would, in this case, have to be 0.896 m. And that's as moles per 0.1 kilogram. So that would mean my moles would have been 0.0896 moles, and 10 grams divided by 0.0896 divided by 0.0896 would be a molar mass of something like 111.6. Now, let's see if any of those would work. Let's beryllium. Beryllium is 9. So 9 plus 35.5 and double it. So that's 80. That's not going to work. The next guy down is magnesium at 24. 24 plus, we'll just say 71. 95, getting closer. Calcium is 40. So 40 plus 71. Whew, that's pretty close. Calcium chloride is 111. So the structure could be calcium chloride, or it could potentially be cesium chloride. It's technically a little bit closer to cesium chloride than it is to calcium chloride, but both of those would potentially work. But so that is an example of how we do it in lab. We will determine our freezing point depression, I, in this case, would be 1. Kf would be given. So we can find our molality from there. Because we will know how much of our salt we had dissolved, how much solvent we used, as long as you don't spill any, we'll know this. And so we can know our moles. And once we know our moles, and you know how much of your solute we've added, we can figure out what our molar mass is. Okay, so that's our lab for the following week, for that February week. Have a good day.